uploaded to, or not to the playlist yet, but I got them on the channel, so I'll get them to the list today. All right, so we left off here at electrophilic additions, this section of the ACS study guide. So let's take a look at question number 1. And it says, what's the major product from this reaction? This is nothing more than the hydration of an alkene. So this is just a hydration reaction. And it is going to proceed with Markovnikov Regioselectivity. So this is a Markovnikov addition, or the rich are going to get richer. This carbon is the one that's got the hydrogen on it. And so it's going to take the hydrogen from our water molecule. And thus the final product is going to look like this, where we've got our ethyl group. So we have our CH2, CH3, and then we're also going to have the hydroxyl on here. So the answer would be B in this case. And you can practice drawing the mechanism for that if you want. It's just a straightforward Markovnikov addition of water across an alkene. The next one, number 2, says, what's the major product of this reaction shown? Remember, when the first reagent is B2H6, something I told you earlier on is that B2H6 is called diborane. It's the same thing as if you used borane and THF. And therefore, first step is the diborane followed by hydrogen peroxide and sodium hydroxide. So this is the anti-Markovnikov addition of water, so anti-Markovnikov. And when we do the anti-Markovnikov addition of water, could anybody tell me, is this a syn addition of the hydrogen and the hydroxyl, or an anti-addition? This is something else that we went over in the hydroboration oxidation. Does anybody remember, is the addition of the hydrogen and the hydroxyl syn or anti? The reason I'm asking you that is because if you look at the possible answers, A has the hydroxyl in the right spot, and B has the hydroxyl in the right spot. C, the hydroxyl's in the wrong spot, and in D, you have 2 hydroxyls, so that's not right. So both A and B are anti-Markovnikov, but only one of them has the hydroxyl and the hydrogen syn, and in the other one, it's anti. So this is anti, and this one is syn. And Nicole's got it. The answer is syn. It's not only anti-Markovnikov addition, but it's also syn addition of the hydrogen atom and the hydroxyl. So the answer would be A. Question number 3 asks, what's the best method to carry out this transformation shown here? So I have an alkene, and then I want to do a Markovnikov addition of water across that. Now, if you look at the conditions, water and aqueous acid will give you Markovnikov addition of water. HBr and peroxides will not. Borane is anti-Markovnikov addition, but we see that D also, so this is oxymercuration, demercuration. It says mercuric acetate and water, followed by sodium borohydride. That will also afford Markovnikov addition. Why would we use D as a condition? What's the stipulation? Like, why would we whip out some mercury to do the Markovnikov addition of water if it can be done with just water and acid? What's the purpose behind this? Exactly. Katie told me it's avoiding or no rearrangement. So then the question is, if you were to use this alkene and treat it with water and acid, would there be a rearrangement? Let's draw the alkene. It's going to be this. I'm just going to draw a bond line structure to make it a little easier on myself. And you can clearly see that if you treat this with H plus and H2O, the carbocation that you're going to form is this. And there's a proton right here. And so you're going to end up doing a hydride shift so that you end up with a tertiary carbocation right here. So that's not going to put the hydroxyl in the right spot. You're going to end up with this compound, okay? Not with the hydroxyl at this position. So in order to avoid that carbocation rearrangement, you would have to use these conditions. So make sure you're very aware of carbocation rearrangements and when you want to avoid them. Let's take a look at question number 4. Question number 4 asks us to predict the product from the reaction shown. We've got HCl, we've got the starting alkene. I don't have a lot of room here, so I'm going to erase this alcohol. Oops, where's my object eraser? There we go. So I'm going to erase this alcohol that we looked at before. And I'm going to, let's just draw a bond line structure. Maybe I'll erase all of this just so I have some more room. So I'm going to draw this starting alkene, which just looks like this. You've got the double bond and a carbon, and then you've got an ethyl group coming off of here and an ethyl group coming off of here. Okay, so that's my starting alkene. I'm going to move it up here just so I have as much room as possible. After it's protonated with HCl, it's the rich getting richer. It's Markovnikov addition. You end up with this carbocation. Remember, there's a proton here, and it's going to undergo a rearrangement to give you this compound where you have the positive charge here. Then you're going to get the nucleophilic attack by the chloride. The chloride is going to go right where that carbocation is, right there, and you're going to end up with A as your final product. So make sure you're able to draw a mechanism of a hydrohalogenation. In that you understand carbocation rearrangements and when they occur so that you're able to predict the major product of a reaction like this. Question number 7. I'll just ask this to my students. Here I have an alkene, and I want to do an anti-Markovnikov addition of water across the double bond. What would be the best set of conditions to use here? Would I use A, B, C, or D? Anti-Markovnikov addition of water across a double bond. So I want to do the anti-Markovnikov addition of water across a double bond. How do we do that? It's not A. There's no conditions that we look at. It's C, right? So this is nothing. A is nothing. This would be Markovnikov addition. But this is hydroboration, boration, oxidation, which is anti-Markovnikov addition. So the answer is C. This is Markovnikov addition as well. Just looked at that a few minutes ago. Okay. It says here the addition of bromine to E3-hexene will give you what? I think it might be wise to take a look at this problem in detail. So we've got E3-hexene, and we're doing the bromination of it. So we've got E3-hexene. So that's E3-hexene. So it's this compound. And then we're doing the bromination of it. So bromine and bromine like that. So we're going to do, I guess I should put my lone pairs in here. There we go. This is kind of a quick mechanism, but first we're going to form the bromonium ion. And our bromonium ion is going to look like this. So I'm going to draw it where you've got the bromonium ion going up like this. So this is our bromonium ion. So you're going to have one ethyl group going in the back. So we're going to have the ethyl group going in the back. Like, maybe I can draw that a little prettier. I'll draw it like this. So it's going in the back like this. And then you've got the other ethyl group coming out in front like that. And now you've got the bromide coming in. So you've got the bromide. And this is the most hindered face of the molecule, the top. So the bromide is going to come in from the bottom like this. And then we're going to end up with something that looks like this. So we're going to have the bromine up here. We're going to have the other bromine that attacked at the bottom, but then you've got an ethyl group going in the back, and you've got an ethyl group coming out in front, like that. All right, so if you were to rotate this, so the two bromines are in the same plane. Whoops. So you have the bromine like this and a bromine like this. So this bromine or this ethyl group didn't move, but this ethyl group that's going in the back is now going to be coming out in front like this. So you end up with a meso compound in this case. A lot of work in this problem, right? You've got to understand anti-addition. So bromination proceeds via anti-addition. And then you've got to be able to rotate that bond and draw the correct compound without having handheld models. So we end up with one meso compound in this case. Oops. One meso compound. Let's move on to question number 11. So question number 11 just says, what is the expected product of this reaction? The first step is a hindered borane. So this is the same thing as using R2BH, followed by peroxides and sodium hydroxide. We have a terminal alkyne. So what we're going to get is the anti-Markovnikov addition of water. So we're going to end up with C6H5, carbon with a double bond, and we're going to end up with a hydrogen and our hydroxyl here, right? So anti-Markovnikov addition of water. Now what I've drawn here is the same thing as this. So C6H5, the double bond like this. But we know that this is an enol. And an enol that's terminal like this is going to undergo tautomerization, give you C6H5. So that's not very pretty. And then you're going to have an aldehyde, oops, like this, which is this compound here. So remember, the enol undergoes tautomerization to give you an aldehyde. So this is chemistry that comes from chapter 9. Chapter 9, the alkynes chapter, just the anti-Markovnikov addition of water across the triple bond. Question 12 says, which molecule will correctly complete this reaction? So now you've got a methyl ketone, and we're using water and sulfuric acid and mercuric sulfate. So this is a Markovnikov addition of water across an alkyne. Not an alkene, not an alcohol, not an epoxide. So the only answer is D, is alkyne. So this is an alkyne, and this is chapter 9. This is the Markovnikov addition of water across an alkyne. And in this case, well, I kind of did leave myself with a lot of room here, but in this case, you would end up again with an enol, but the enol that you would end up with would be this enol, where you would have, this double bond, okay? And this enol is going to undergo tautomerization to give you the methyl ketone. All right, so this is the Markovnikov addition of water across the triple bond. Let's try two more. So question 16 is this one here. Hey, I'll just throw this out there to my students. Question 16, you're going from an alkene. So this is an alkene. And you're going to an epoxide. Another name for an epoxide is an oxirane. It says, which reagent would be best used to complete this reaction? Could anybody tell me what the best answer would be here? In 16, how do you make an epoxide, a three-membered ring with an oxygen in it? Right, we've seen this only in one place ever before. It's when we were taking an alkene, like let's say you took this alkene that we're starting with here, and what we did was in step 1, we treated it with RCO 3H, which is the same thing as MCPBA. Okay, that's just a type of peroxy acid. And what that does is it makes the epoxide like this. And then we treated that with, in step 2, with H3O plus, and that breaks the ring open so that you end up with a trans diol. You get anti-addition of 2 hydroxyls. All right, so again, this is from chapter 8, anti-dihydroxylation, hydroxylation. And the way that is done is in the first step by treating it with RC3OH, which makes the epoxide, and then that's opened with aqueous acid in the second step. So that's what a peroxy acid is for. So RC3OH is a peroxy carboxylic acid or a peroxy acid. All right, let's do one more before we end our lecture today. Question number 19 is halohydrin formation. So this is halohydrin formation, which comes from chapter 8, the alkenes chapter. We're taking an alkene and we're treating it with bromine and water. So we make a halohydrin. What happens is first you make a bromonium ion. So in this case, your bromonium, I don't have a lot of space, so I'll scribble it down here. You would end up with, let's just draw the methyl group going down. And in this case, you end up with a bromonium like this. Okay, and then in the next step, water, which is your nucleophile, is going to attack. But remember, it attacks at the more hindered carbon like this. So you end up with anti-addition of the bromine and the hydroxyl. So the answer can't be A because the bromine and the hydroxyl are in the same place. In B, they're anti to each other. In C, they're anti to each other, right? But the hydroxyl is not at the most substituted position. It's at the less substituted position. And here they're syn to each other. So the only possible answer is B because it's anti-addition, and the hydroxyl is at the most substituted carbon. So again, if you need to review it, it's halohydrin formation, which is covered in chapter 8.